This week, we're going to be transitioning from the computer vision portion of the class to the computer graphics portion of the class. In today's lecture, we're going to go over a high-level overview of what computer graphics is and some of the topics that we are going to be covering for the remainder of the semester. We're going to start by giving a very high-level overview of computer graphics and some of the applications that computer graphics can be used for. We'll then introduce a simple definition of what constitutes computer graphics, and then we'll go over some of the common challenges that we're going to face when trying to tackle various problems in computer graphics. After that, we will go over some of the main topics in computer graphics that we are going to be covering in the second half of the semester, as well as some logistics for the graphics portion of this course. To start, let's take a look at what is computer graphics. So one way that we can define what computer graphics is as a field is in the broader context of visual computing. At the very start of the semester, we introduced visual computing as consisting of two main subfields, computer vision and computer graphics. So far in this course, we focused primarily on computer vision. And in vision, the problems that we are often interested in can be posed as taking some sort of visual input, like an image or video, and we want to be able to extract a computational model of the contents of that image. An example of this might be to look at a photo and try to identify all the objects that are being shown in that photo. So given a visual input, the goal of computer vision is to try to extract some representation of the contents of that image. Computer graphics, on the other hand, can be thought of as the inverse problem of computer visions. Instead of being given visual inputs, in computer graphics, we are provided with a computational model of a particular scene. So the input to a computer graphics system would be some representation of, let's say, the objects that are in the scene, or the characters or the locations of a scene. And the goal of computer graphics is to take that abstract representation of a scene and generate an image or video, a visual representation of that scene. So rather than starting from images and then extracting a model from those images, we're going to start with a model, and we then want to produce images or videos of that model. So to give you some concrete examples of the types of problems that we might be interested in computer graphics, let's take a look at some applications where you might find methods that are developed in computer graphics. And if you think of computer graphics applications, probably the first example that most of you will think of would be applications in visual effects and video games. So on the left, we have an image of a computer animated movie. And in this case, with Super Pets. And the thing to note about these images is that the characters and the objects that we see in those images, they don't really exist in the real world. Instead, these images started out as just computational models of the characters of the scene. And we then developed algorithms that allow us to generate realistic images of those objects and characters. For applications in visual effects, this requires us to develop techniques that can produce very realistic, very high fidelity images that look like images that we might expect to see in the real world. On the right, we have an example of a screenshot from a computer game, in this case on Final Fantasy VII. And this is an example of a real-time application of computer graphics, where we not only have to generate realistic images, but we have to be able to generate those images at a very fast frame rate, like 30 or 60 FPS. So as a as an example of what you can do with some of these modern computer graphics pipelines. Let's just take a look at a quick demo here.
Don't fail me now.
So this is one example of what some of these real-time computer graphics systems can do. So everything you see so this was a demo that was created for Unreal Engine 5, a little bit older at this point. But everything that you see on screen, all of the geometry, all of the lighting, the rendering, the animation, all of that is being done in real time. So this is an example of an application where we not only have to produce realistic visuals of a scene, but we have to be able to produce these very high fidelity images at a very fast interactive frame rate. And in order to do this, these real-time graphics applications require some of the cutting-edge techniques in computer graphics. Now, beyond applications to visual effects and video games, computer graphics techniques are also widely used for data and scientific visualization. So when scientists are analyzing large complex data sets, it's often very useful to construct visualizations of those data sets that can help analysts try to decipher patterns or trends from those complex data sets. So for example, on the left, we have an example of a visualization of the airflow or the surface of a space shuttle during takeoff. And then on the right, we have an example of the visualization of demographics and population statistics for different countries over time. And by leveraging computer graphics techniques to visualize these complex data sets, they can help analysts and policymakers to try to decipher trends in those data sets. So as one example of this, let's take a look.
For health, life expectancy from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only the UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now,
okay, yeah. So for those of you who haven't seen this video in its entirety, I think it's really worth checking out. It's a really nice example of data visualization, where by leveraging computer graphics techniques, we can display complex data sets in a way that can be very intuitively understood by a broad audience. Now, another common application of computer graphics that you see everywhere nowadays is in computer-aided design and fabrication. Most of the things that we see around us, from buildings to objects to devices, most of these structures were first designed on a computer before they were constructed in the real world. So in order to prototype and design these objects on a computer, we rely on geometric modeling techniques that allow us to represent the shape of complex objects in a computer, as well as to provide tools that allow designers to iterate and modify these designs. Now, perhaps a slightly more recent application of computer graphics are things like virtual reality and augmented reality, where we try to create these realistic real-time experiences that can be overlaid on the real world. And finally, another more and more common application of computer graphics that might be perhaps a little bit less well known is in the development of artificial intelligence and robotics. More and more common nowadays, many of the AI systems that we see around us, they're often prototyped or were trained using data created in simulation. And in order to create these realistic simulations of different objects and scenes, this often leverage techniques developed in computer graphics, in geometric modeling, in physics simulation, and also in animation. So for example, if you want to develop a system for a self-driving vehicle, then you probably want to prototype the system in simulation, test it out thoroughly before you run it in the real world. Well, another example of this is in robotic learning, where oftentimes before, in order to train robots to do different things, like in the real world, like walking or maybe martial arts and acrobatics, we will often train these robots in simulation before deploying them in the real world. And to produce these realistic simulations of these robots, we will often be making heavy use of techniques developed in computer graphics. Good. So those are just a few samples of the wide variety of applications of computer graphics. Any questions about this before we move on? Okay. So given the diverse applications of computer graphics, it can be a little bit difficult to come up with a comprehensive definition of what computer graphics is as a field. So in this class, we're going to work with a very broad definition of computer graphics, where we're going to say that graphics is an area of computer science that studies techniques for how to use computers to create and interact with visuals. Okay, so this is a very broad definition, but to give you some idea of the types of problems that people are interested in computer graphics, we can take a look at some of the research that's been presented at SIGGRAPH. So SIGGRAPH is the largest annual conference on computer graphics, where the latest research in computer graphics is being presented every year.
Hello, and welcome to the SIGGRAPH 2025 Technical Papers trailer, where we showcase some of the amazing research being presented at this year's conference. Check out the illuminating technical papers at SIGGRAPH 2025. Switch on and off light sources in an image, or even change their color by using a diffusion model fine-tuned on both real and synthetic lighting data. Want to fix lighting in a picture? This method can relight single images with anything from distant environment maps to local point lights by using an estimated proxy scene to guide neural re-rendering. Look your virtual best in any lighting environment with a relightable full-body Gaussian codec avatar, which uses a local global light transport split to more accurately capture illumination effects. Want to go beyond relighting? Diffusion as Shader generates videos by using a 3D point cloud as a diffusion model input. This allows for camera movement, mesh to video generation, and object editing. Edit videos with text prompts and sketches. This system propagates single-frame edits by using a 3D point cloud to handle camera transformations and a diffusion model to synthesize a seamless final result. Speaking of consistency, scenes aren't soups. This system does 2D to 3D reconstruction using inferred spatial relationships between objects, producing physically plausible arrangements and enabling occlusion-aware object reconstruction. This paper shows how to represent dynamic objects in video generation by first fine-tuning on appearance and then on motion. The resulting dynamic concepts can then be combined with other prompt data to control generated videos. This paper shows how to infuse albedo, normal, and roughness textures with details such as wear, aging, and weathering by using an off-the-shelf diffusion model. The output is another texture set, amenable to further editing and adjustment. Speaking of materials, sometimes you can have it all. Comprehensive Neural Materials uses a quantized neural network to represent high-performance, high-fidelity materials with user-controllable synthesis and parallax effects. Want to get hands-on with 3D creation? VRDo is an open-source VR modeling system that lets users sculpt and edit objects using their own virtual hands. We know 3D Gaussian splatting shines, and now it shines through. Transparent GS introduces transparent Gaussian primitives with deferred refraction for precise reflection and refraction effects. Now you can paint with 3D Gaussian splats. This paper describes tools to select groups of splats, deform and stamp them along a brush path, and even do inpainting for seamless connection to the underlying scene. Gaussians too smooth for your 3D scene? Deformable beta splatting replaces Gaussians with beta kernels, which allows more precise geometric representation.
Well, I guess well, hopefully this will give you some idea of kind of the different types of research that people are doing in computer graphics. So graphics is a very broad field, and then lots of people are looking at a very wide range of different problems. So if you want to dive deeper into computer graphics, SIGGRAPH is a very good resource to try to give you an overview of the types of different problems that people are interested in. So this is an archival website that contains links to all of the papers that have been presented at SIGGRAPH each year. So you can take a look through this to see some of the papers that have been presented at the conference. Now, one of the really nice things with SIGGRAPH is that most of the papers are accompanied with very well-produced videos. So even if you don't read the paper, even if you don't look into all the technical details of the paper, you can just look at the videos, and that can give you a pretty good sense of what the main ideas are for that particular paper. So for those of you who are interested in going further in graphics, SIGGRAPH can be a very valuable resource. Okay. So now let's go back to our definition of computer graphics and try to analyze this definition in a little more detail. We say that computer graphics is an area that studies the use of computers to create and interact with visuals. And I've highlighted a couple of keywords here, and we can take a look at each one of them in a bit more detail. So to start, for most of computer graphics, we're often interested in processing visual data of some form. And when working with visual data, this usually means big data. To store high-resolution images and videos or meshes requires a large amount of memory, and processing those large volumes of data can be very expensive. So when we are working in computer graphics, when we are developing algorithms, we often have to take care to try to design efficient data structures and algorithms that can be applied effectively to these large volumes of data. Now, the second keyword is interact. For a lot of applications in computer graphics, we often need to be able to apply those techniques at very fast interactive frame rates. So if we are applying techniques in a video game or applying techniques to a tool that's going to be used by a user, we often need these methods to produce not only high quality results, but they have to be able to produce those results at a very fast interactive frame rate. And this introduces further challenges to ensure that the techniques and the systems that we build are very efficient. Now, the last keyword that we've highlighted here is create. Many of the techniques that develop in computer graphics will eventually be incorporated into tools which will be used by maybe less technical users in order to produce visual content. Which means that when we are designing tools, when we are developing algorithms, we have to take care to introduce techniques that will allow users to control the output of those algorithms. So you might create a very powerful system that can produce very realistic images. But if there's no way for users to use that system to produce the images that they want, then it's not really going to be very useful for anyone. Therefore, when developing algorithms and methods in computer graphics, we often have to introduce ways that will allow users to control and use the outputs of these systems. Okay. So this definition highlights some of the common challenges that we'll face in computer graphics. And these challenges are going to reappear again and again as we discuss the different topics over the over this course. But any questions about any of this? Then let's take a look at the main topics that we're going to cover for the computer graphics portion of this class. We're going to, so the lectures are going to cover three main subfields in computer graphics. We're going to start with modeling, where we are going to take a look at data structures and algorithms that allow us to represent as well as to process 3D shapes. In this section, we're going to introduce different data structures like polygon meshes and implicit representations that will allow us to represent 3D objects on the computer. Once we have a way of representing 3D shapes, we'll then take a look at rendering algorithms, which will allow us to take those 3D models and generate realistic images of those objects. And then after that, we're going to take a look at computer animation techniques that will allow us to go beyond generating static images and be able to produce dynamic animations and videos. So these are the three main subfields of computer graphics that we are going to go over. And this is a list of some of the specific topics that we'll be covering. Okay, so today's lecture, we had a quick introduction of computer graphics, and then we're going to have a quick review of image representations next class. After that, we're going to start moving into the geometric modeling of this class, where we'll introduce different data structures and algorithms for representing and processing 3D shapes. After that, we're going to go over the longest section of this class, which will be on rendering, where we're going to cover different rendering techniques like rasterization and ray tracing, as well as different lighting models. And then at the end of the course, depending on how much time we have left, we're going to go over some topics in computer animation. Now, that being said, this schedule is tentative, and we might shift and add and remove topics depending on how timing works out for the rest of the semester. Okay. Any questions about any of these topics? So these are the topics that we're going to cover in this class. And now I want to briefly cover what we are not going to be discussing in this course. So this class is going to be about kind of the fundamentals of computer graphics, but we are not going to teach you how to use computer graphics software. So if you want to learn how to use things like Blender or Photoshop, then chances are we are not really going to, this course is not really going to cover topics in that. But if you want to build your own Blender or Photoshop, then the topics that we cover in this class will be useful for that. Okay. So those are the main topics that I want to cover for this introductory lecture. And I just want to wrap up by going over some of the logistics for the second half of the semester. We do have a textbook for the computer graphics portion of this class. There's a link that's available for kind of a free PDF version of this book. And for the most part, this textbook is mainly as supplementary material to the lectures. All the assignments and exams are going to draw from topics that are covered during the lectures, which means that if a topic is in the textbook but was not covered in the lectures, then for the most part, you don't really have to worry about that. The textbook is mainly there if you want to dive deeper into some of the topics that we do discuss during class. So I'm also going to be holding our weekly office hours via Zoom. It's going to be on Mondays from 2 to 3. And the TA for the computer graphics portion of this class is going to be Matthew. And he'll be holding weekly office hours in person at L9014. Now, similar to the computer vision portion of this course, there will be video lectures available on the course webpage. And The in-person lectures are going to be a little bit different than the video lectures. We're going to go into similar topics, but in more depth. But unlike the video lectures for the computer vision portion of the class, they'll be optional, which means that you don't necessarily have to watch these lectures before you come to the in-person lectures every week. The in-person lectures will more or less cover the same material as the video lectures, but we'll just dive into some topics in a little bit more depth. But you can use the video lectures for maybe as additional supplementary material for, let's say, your assignments and exams. There will be 2 assignments for the graphics portion of this class. Assignment 3 is going to be due on March 25th, and then assignment 4 is going to be due on April 15th. So there's still a lot of time before the third assignment is due. You don't have to worry about that for now. We'll discuss the assignment in more detail later on once we've covered more of the relevant topics. For all of the assignments, we provide you with a fair bit of template code. So for the most part, you just have to fill out a few functions. Now, so the template code is also going to be linked on the course webpage. But again, don't have to, no pressure to start on the assignments now. We'll talk about the assignments more later. Okay, then the last little bit I want to cover for today are going to be some information about the final exam. The final exam is going to be in person, and it's going to be on April 23rd, 3:30 to 6:30. And it's going to be located at WMC 3520. The midterm focus primarily on computer vision. And for the final exam, most of the focus is going to be on computer graphics. So roughly 25% of the marks are going to be allocated to computer vision, and then the rest of the points will be allocated to computer graphics questions. So most of the focus will be on computer graphics, and the exam is going to be cumulative, which means that we're going to draw from anything that's covered over the course of this whole semester. So any topic that's covered in the midterm can still appear in the computer vision portion of the exam. The exam is going to be closed book, so as usual, no devices, no cheat sheets, no computers, so on. Okay. What does it mean? Oh, your question.
The in-person lectures recorded?
Yeah, they are recorded and we'll post links on courses as well. Yep.
Regarding studying for the final exam, you said that any midterm might after a final, will we have access to our midterms, so it will be over, or does this class be final?
We are not going to return the midterms, but then I think Yagis will arrange some sessions later where you can review the midterms. Yep.
Logistical question. I know this is like for period over thing, but you know when they're going to upgrade that for the midterm?
Oh, they haven't been released yet. I think they should be released pretty soon. If they haven't been already. Okay. Yeah. This is mainly everything that I wanted to cover today. Any questions before we wrap up? Okay. If not, then I'll see you on Friday.